Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, here we go with today's lesson is on investigating probability, lesson 1.2.2. Nothing to front load here. We've already talked a little bit about how probability works, so we are going to just jump right into it. So, have you ever tried to predict which football team will win a big game? If so, you probably did not just pick the team with the coolest colors or the neatest mascot. You may have based your picks on statistics about win-loss records, player injuries, and other data. Knowing what has happened in the past can sometimes help you predict what will happen in the future. In this lesson, you will use data to make predictions. As you're thinking about things, to uncover a mystery spinner, keep the questions below in mind. What is the probability or likelihood of something happening? What do you expect to happen? How does the actual event compare to our prediction? And what can we know for sure? All right. So the way that this works is I have created a spinner on my on this program. Unfortunately, because you're not in class, we have to do this slightly differently. So in class, what I would do is I would turn off the TV screen and I would spin the spinner, and everybody in class, I would tell what color came up after I spun the spinner, and everyone would record how many times each color came up. Okay. And then what we do is people predict what the spinner looks like and draw a representation of what they think the spinner looks like in their journal. Okay, I can't do that because you're watching the video and every time I spin it, you would see exactly what the spinner looked like. So that's not going to work. So I have already done this. Behind this box is the spinner with 3 different colored tiles, or wedges, I guess is what they're called, wedges. The 3 colors are purple, green, and orange. Okay. Now, I spun already and recorded how many purple came up, how many green came up, and how many orange came up after 12 spins, after 24 spins, after 36 spins, and after 48 spins. And I chose these numbers because these are the numbers that have lots and lots of factors. And so it makes it easier to write ratios as fractions and simplify them when we're dealing with this as a denominator. Because, 2 goes into 24, 3 goes into 24, 4 goes into 24, 6, 8, and 12, and of course 24 goes into 24. So you got a lot of different possible simplified fractions you can get when we're dealing with these numbers as denominators. So that's the reason why I chose these instead of choosing like 10, 20, 40, 80 spins. Okay, so this is the results after 12 spins. 7 of the spins were purple, 3 were green, and 2 were orange. So if you were to write those as ratios, remember the total number of spins, that's the number of possible outcomes, goes in the denominator, and the desired outcomes, did you desire purple or green or orange, those would be the numerator. So 7 out of 12 is equivalent to about 58%. 3 out of 12 is exactly 25%, and 2 out of 12 is the same as 1/6, which would be 16 and 2/3%, so I just rounded it up to 17%. Okay, so if you were thinking about what this would look like as a spinner, if all the wedges were equal parts, you would think there would be 7 of them. 7 out of the 12 would be purple, 3 out of the 12 would be green, and 2 out of the 12 would be orange. All right, now after spinning 24 times, we'll see if these percentages hold or if they shift a little bit. Because as you may recall from our previous lesson on probability, the difference between experimental probability and theoretical, and this is experimental because we're actually spinning the spinner and keeping a tally of what the results are. That's what makes it experimental. We're expecting the true probability, the true theoretical probability to emerge the more times we do the experimental probability. So right now it looks like the probabilities are, or the chances are 58%, 25%, and 17%. Let's see how that changes here when we do 24 spins. All right, so looks like the green stayed the same at 25%, and purple reduced a little bit to 50%, and orange climbed to 25%. So if I were thinking about what this might look like, I could actually draw a little representation of what I think this might look like. I might think, which color should I use? I'm going to do this. Looks like half of them would be purple, right? So this might be purple, this might be purple, that's 2 out of the 4, right? That's half. And then this could be orange, that's not a Q, that's an O. And this would be green, right? So those are what the percentages look like right now. And those are nice, neat percentages for breaking your circle or your spinner into different parts. But that's after 24. That doesn't necessarily mean that that's 100% accurate, okay? Get rid of you, I don't want you there now. But that's the idea. All right, now let's see with 36 spins what happens with our percentages. After 36 spins, 17 out of the 36 were purple, which is still pretty close to half, right? A little bit less than 50%. The greens increased to 12 out of 36, which is 1/3, which is 33%. And the orange took a dip. Looks like it went from 17 to 23 back down to 19. We see our percentages of green increasing, our percentages of purple are decreasing, and the orange is kind of going back and forth a little bit. And now after 48 spins, what do we have? All right, so it looks like the purple, which started off at 58%, went down to 50 and is holding really close to 50% at 48%. The green, which started off at 25%, has increased to 33%, and it's held there. And isn't that interesting that the essentially the percentages stayed the same for the 36 to the 48 spins? So, based on these percentages, your job now is to. Are we supposed to do it yet? We're supposed to do it yet? No, I think we're supposed to do it now. Okay, sorry about that. I wasn't sure if there was another question we needed to get to first. I would like for you to draw what you think based on this one right here, the 48 spins, because that's the most. Remember, the more times you conduct the experiment, the closer you get to your theoretical probability. So what do you think the spinner may look like? Okay, go ahead and draw that. And then I'm not going to reveal yet. I'm going to have the big reveal at the end. Seems like we should make this as exciting as possible. Go ahead and pause your video and draw a circle and decide how many wedges you think would be ideal. Please don't make one that has 48 wedges or 24 wedges. You know, estimate these percents, round them off so that they make nice, nice good percents that can be simplified down to you know, either 4 equal parts or 6 or 8 or 12 equal parts. All right, so after you've done that, you unpause and you come back to me here. What do we have going on here? It says use the data you collected in the previous problem to answer the following questions. Based on your data, how can you describe the likelihood of landing on each part of the spinner? How does the spinner that your team drew represent these likelihoods? Okay, so that would be the one that you drew. And so obviously it's not impossible, right, to get purple, green, or orange, because we got them all. And it's not certain that you're always going to get purple or green or orange. So in our likelihood spectrum, all of them fall into that possible, but not certain, okay? So I guess what I would say is this. I would say, oh, did I say blue? I meant purple. When I was looking at it, I thought it was blue. Hold on, purple. Okay, there we go. I hope I don't have to make that change somewhere else. Oh, there's the purple right there. Okay, so purple's the most likely, right? Because that was the highest percent. It was 48% after 48 spins. And green was in the middle at 33%, and orange was the least likely at only about 19%, according to our experimental data. So use your data to write the experimental probability of each of the following. Start by writing it as a fraction. You already have it as a percent, but try and convert that to a fraction and then as a decimal. Okay, so starting off with spinner lands on purple. Let's use this one right here. How many spins did we do? That would be your denominator of your fraction. And how many times did it land on the purple? So write this ratio. You've got the percent, and then convert your percent into decimal form. If you really technically want the exact decimal form, it would be 0.47916 repeated, but who wants to write that? It just seems like it's more logical to round that up to 4800s, right? 0.48 or 0.479 if you want to call it 47.9%. You could just do those first three decimal numbers. Okay, so with that in mind, you should have listed that the fraction probability is 23 out of 48, which is 48 hundredths approximately, rounded up, and approximately 48%. But in the grand scheme of things, if we wanted to round it up even more, wasn't it really hovering around 50%? It was at 58, then 50, then 48, then 48. So it's about half, right? About 50% of our spinners should be purple. And then the green and the orange. Well, the green was 33% and the orange was 19%. So when you add those two together, of it landing on either green or orange would be about 52%. So 25 out of the 48 times we spun the spinner, it landed on either green or orange, which the decimal equivalent to that is it rounds to 52 hundredths, which is about 52%, which is also, you know, if you added 2% to this to round it up to 50%, take away 2% from that. So it looks like half the spinner, about half the spinner is green or orange, and about half the spinner is purple, which actually is exactly what we've got right there. Isn't that interesting? Although I'm not quite sure that these ratios of the green and the orange are accurate. These probably are more accurate. All right, so if you were to spin the spinner 15 more times, how might this change your answers for part B? Would you expect them to change? Would you expect them, what would you expect? And so the answer to that is, you know, experimental probability. The more times you do it, you expect the probabilities to become more accurate to the actual theoretical probability of the spinner. So do you know for sure what your spinner looks like? Is there any way to know for absolutely certain exactly what it looks like? The answer to that is not really, but it should be pretty close, right? The more times you do it, the more accurate your probabilities should be. So you should have something that's fairly close. Now, based on what I was saying here, if I were to draw the spinner, dooby-dooby-doo, I would say, all right, so let's go like this. Half of it would be purple. And what is this? Is this showing, does that look like 33%? That's 1/3, right? So what would 1/3 look like? Something like this? No, that would be like 1/3. That's 1/3 of the circle, right? Purple, 1/3 of the circle, so that would be green. And then you've got the rest of it is orange. Okay, so if we went with that, half of it is green and orange, half of it is purple. And of course, I'm blocking them all together. We could have these wedges, like you could have a purple wedge here and a purple wedge there and a purple wedge down here. It could be all over the place. That's not what we're going for. We're going for the ratios, not the precise placement of each one of the colors. Okay, just so that you know that. All right, so now your teacher will reveal the mystery spinner. Big reveal. Hidden spinner. Bye-bye. And there it is. Exactly I must have subconsciously known what it looked like and drew it in this way. But yeah, that's it. That's the spinner. 3 out of the 6 wedges that I created for this, which is 50%, are purple. 2 out of the 6, which is 33%, or 1/3, are green, and then the rest of it is orange. So if you took away some of this 19% and dropped that down to about 16 or 17%, 16.7 rounds up to 17. So take 2 percentage points from that and put it up to here, and we would have had the exact probabilities, the exact chance of landing on each one of them. Do your spinner and your teachers show the same likelihood? Hopefully they came pretty close. All right, so one way to compare your spinner to your teacher's spinner is to calculate the theoretical probability for each colored section of your teacher's spinner. What are some reasons the experimental probability and theoretical probability for each section could be different? Well, you never know if you're going to get your experimental probability perfect. Okay, sometimes you do, but we could spin it 100 times and get everything perfect, and then spin it 200 more times, and then the percentages could be slightly off. Remember, in theory, the more times you do it, the closer it gets to experimental, but you could have it perfect after 6 spins. That could happen. And then you do it 12, then you do it 24, and it goes off a little bit. But by the time you do it 1,000,000 times, your percentages are going to be pretty much accurate. So estimate the theoretical probability for getting each color. So remember what that spinner looked like? Remember how 3 out of the 6, which is the same as 1/2, were purple? 2 out of the 6, which is the same as 1/3, were green, and 1 out of the 6 were orange. So those would be the theoretical probabilities. And just for the sake of writing down the percent, this is the same as 50%. This is the same as 33 and 1/3%. And this is the same as 16 and 2/3%. So we had 33%, it was really 33 1/3. We had 19% when it was really 16 and 2/3%. Here we had 48 when it's really 50%. So how do experimental probabilities and the theoretical probabilities compare? Well, they're close. The more times we spun the spinner, the closer everything became. All right, so now we're going to get into a fundamental understanding of how probability works and how we use it for problem solving. Let's just make sure we've got all of these over here. The probability of getting orange was 1 out of 6, correct? So what we expect, if we spin the spinner 48 times with this probability, we expect 8 out of 48 times for the orange to come up. Now, how many times did the orange actually come up? It actually came up 9 times, 1 more than we expected, which is why this is a little bit more than 16 and 2/3%. When we spin the spinner 48 times, if we expect 1 out of every 3 times we spin the spinner to be a green, then we would expect 16 out of the 48 times for it to be green. And I believe that's exactly what happened. I just rounded it off to 33% when it was really 33 1/3%. But that's what we expected according to these ratios. If 2 out of every 6 times you expect to get a green because of the theoretical probability, then 1 out of 3 times you would expect a green, and 16 out of 48 times you would expect a green. So this process of setting it up as 2 equivalent fractions is called proportional reasoning. And we'll talk more about strategies for how to create equivalent fractions based on probabilities and proportionality. Now for the last one, we expect, since half of the spinner is purple, that 1 out of every 2 times we spin it, we're expecting a purple to be the color that the spinner lands on. And so if we spin it 48 times, we expect it to land on the purple 24 times. As it turned out with our experimental probability, it actually landed on it 23 times, which is really close. Okay? Remember, This is what you expect, not necessarily what is absolutely going to happen. So for this question, if you were to spin the spinner the number of times listed below, the 6 times and the 48 times, how many times would you expect it to land on orange? And so orange, the probability is 1 out of 6, so you expect once out of every 6 spins it'll land on the orange, and 8 out of 48 times it would land on the orange. So with that being the case, how many times do you expect it to land on orange if you spin it 100 times? Well, our ratio or our probability is 1 out of 6, correct? What we need to do is set this up out of 100. So if you spin it 6 times, you expect orange to come up once. 12 times, you expect it twice. 18 times, you expect it 3 times. There's a multiplication process to this. So how do you find an equivalent fraction to 1/6 with a denominator of 100? Well, if you take 100 and you divide it by 6, that's where you get your 16.6 repeated. So I rounded it up to 16.7. So this is the whole giant 1 idea. Whatever you multiply times the numerator to give you this numerator, you multiply the same thing times this denominator to get that denominator. So 16 times 7 is what you're going to multiply times 6 to give you 100. So that's what you'll multiply times 1 to give you this number here, which means we're going to expect if we spin this spinner 100 times, we expect between 16 and 17 oranges to pop up. And that's what the percent is, right? 16.7%. Percent means out of 100. All right, switching gears, we're almost done. How much time have we used up? All right, we're going to be done with this in a few minutes. Rachel and her little sister Christy often argue about who should wash the dishes at their house. Rachel suggests that they flip coins to solve this argument. Flipping the coin is fair since heads and tails each have an equally likely chance of happening. Each one has a probability of 1/2, or 50%. Rachel says, if the coin shows heads, then I'll do the dishes. If it shows tails, you do them. So, is this fair? Is Rachel's suggestion a fair suggestion? What is the theoretical probability of getting heads and for getting tails? Well, heads is 1/2, tails is 1/2. She said it right there. Each one has the 50% chance and the 1/2 probability of being flipped. So yeah, that's a fair game. There's an equally likely chance that either one of them on any given day will do the dishes. Rachel and Christy flip a coin every evening for the first week. That's 1 week, 7 days. Christy has washed the dishes 4 times, and Rachel's only washed the dishes 3 times. Now Christy is upset. She's like, it's not fair. She had to do the dishes more than Rachel. Is she right? What do you think about that? Well, she's right and she's wrong. It is fair, that's the part where she's wrong, but she is right. She did have to do the dishes more than Rachel this week. Why? Well, there's an odd number of days in the week. You're never going to have, after a full week, both of you doing the dishes the same number of times. And so the reason why Christy did 1 more than Rachel is because the 7th day. Most likely after 6 days it was even. But on the 7th day, one of them had to do it, which made it unequal for the week, simply because there were an odd number of days. So after the 2nd week of coin flipping, Christy washed the dishes 10 times. And Rachel had only washed the dishes 4 times. Now she's really mad. Christy is really upset because she has washed it so many times compared to Rachel. In light of this new information, do you still think it's fair or not fair? What would you recommend to Christy? I know what I would recommend. I would suggest she stop complaining and just play the game. Because you know what's going on here? This is an example of experimental probability. Just because you've got a 50% chance of heads coming up and a 50% chance of tails coming up on any given flip doesn't mean that they're going to alternate. You could have 5, 10 heads in a row. That'll happen. If you only flip the coin like 20 times, you could get 15 of them be tails and 5 of them be heads. However, what is going to happen eventually over the course of a year, it's going to even out. The game is still a fair game, even though after 2 weeks, it didn't equally distribute the work for Christy and Rachel. But over time, it eventually is going to even out, and there's going to be time where Rachel ends up having to do more dishes in any given week than Christy. So that's how probability works. We'll be practicing more of this as time goes on throughout the year. So hopefully you've been able to take good notes and this all made sense for you. If there's ever a time when these math notes from the videos aren't making sense, please feel free to send me an email and we can correspond back and forth. Or if you come back to class, we can talk about it during class time as well. All right, good luck on the homework. Take care. And 25 less than 26 minutes. Good job. Okay, bye.
Hey, feeling good, like I should.